Chapter 8 deals with nuclear chemistry, and again we're going to look at kind of an abbreviated version of this chapter. We're not going to need to know absolutely everything from it. There's a lot of interesting information here, but what I want you to be able to deal with are the type of reactions that we can actually see in a nuclear chemistry reaction scheme. Now, the main thing to remember about the basics of this chapter is that we have a process referred to as radiation. And what this means is that we have certain particles or energy that come out of the nucleus of atoms, and that comes out with energy of its own, and that emission is referred to as radiation. Now, the study of radiation and the processes that make radiation occur is referred to as nuclear chemistry, because all of these processes that cause radiation are typically happening inside the nucleus of the atom. Now, in this case, before we've looked at just a rearrangement of attachments of one atom to another, in nuclear chemistry, because we're actually fooling around with the nucleus of the atom, we have the potential to change the number of protons present, which, as we know from our previous discussion, actually changes the element that we're dealing with. So as opposed to what we looked at previously with chemical reactions, we can actually end up changing one element to another. So it's important enough that we need to point this out. Okay? Up until now, molecules change because electrons rearrange. Either we have movement of electrons, which is an ionic bond, or we have sharing of electrons, so we have a stable octet electron configuration. But either one of those things doesn't mean that I change from having hydrogen to helium or lead to gold. All that happens is that my attachments change because the electrons change. But now in nuclear chemistry, the atom actually has changes inside of the nucleus, or the nuclei is the plural of nucleus for the different atoms. And when this happens, we get these radioactive particles emitted. The three types of radiation that we're going to look at, and there are more than this, but these are the most common that we'll run into, are alpha, beta, and gamma type radiation. Now, all alpha radiation is a helium nucleus being fired off from inside the nucleus of another atom, and this chunk that comes loose takes with it 2 neutrons and 2 protons. Okay, so 2 neutrons and 2 protons is a helium nucleus. Now this has a lot of mass to it, so when this comes flying out of the nucleus and strikes into something, it has the ability to do a lot of damage to whatever it strikes. However, since it's so big, it's not really going to get through material to get to the skin to do damage. And in fact, thick clothing can isolate you from a lot of alpha type radiation effects on skin. Now, beta radiation, symbol here is the Greek B, just like for alpha, the Greek A symbol we use. This is actually an electron. And we'll go over in a minute here when we talk about beta radiation why we give this the particular isotope numbering system that we do. But in reality, all it is an electron coming out of the nucleus of the atom. Okay, so that electron actually occurs because a neutron is turning into a proton, and as it does so, an electron is kicked out of that. But the ionizing power of this, in terms of the amount of damage that can be done by this particle, is less severe than the helium nucleus because this is a much smaller particle. However, it has a lot more force, typically going a little farther, and not more force, but more speed, and that can lead to, in addition to its smaller size, more penetrating power for that particular type of radiation. So it can get through clothes, it can get into the skin, it can do more damage. Now, gamma radiation, as we know from our light chapter, is not actually a particle. This is actually just electromagnetic force, radiation, in the range that gives us gamma energy. So this isn't a lot of energy. This is a lot less energy than being smacked into by 2 neutrons and 2 protons, or being struck by a fast-moving electron, but it still has some ionizing power. This can still cause damage. And one of the main reasons that this is dangerous, even though it doesn't cause a lot of direct damage to what it hits, is that it can penetrate deeply into the skin and hit things like our DNA and that sort of thing, and cause changes and issues there. So what actually is alpha radiation? Okay. So these alpha particles, this helium nucleus, we can represent by helium 4-2, right? And this 4, don't forget, is the number of protons plus the number of number of neutrons. And the 2 at the bottom, the atomic number, is just the number of protons. So that means that this helium nucleus has 2 protons and 2 neutrons. So that's why we represent this by a helium nucleus. Now, when this happens, if we look at the nucleus of, say, a uranium-238 atom, which has 92 protons and a large number of neutrons, whatever 238 minus 92 turns out to be, number of neutrons. Now, when this undergoes alpha decay, that means that alpha radiation is given off, and the nucleus of the atom that is giving off alpha particles as radiation changes. So if I lose 2 neutrons and 2 protons as a chunk from this particular atom, that means that I've lost 2 protons and 2 neutrons. Okay, so we go from 92 from the uranium over here down to 90 protons. Right? That accounts for these 2 protons there. And so 2 comes off of this top number. But in addition to that, we also lose 2 neutrons as well. So we lose 4 particles altogether out of this top number, the atomic mass number. So 238 goes to 234 for the top number. Now, one thing I want you to notice is that 234 plus 4 gives me 238, which is what I started with. 90 plus 2 for the atomic number gives me 92, which is what I started with. When we talk about balancing before, we were talking about the number of each type of atoms. But when we talk about balancing nuclear chemistry reactions, we're talking about balancing the atomic mass number, that number on the upper left-hand corner, and the atomic number, the number of protons. And so those are what I have to balance in order for a nuclear reaction to be balanced. And notice we changed from uranium to thorium, as we changed into a completely new element just by this type of decay. So we can look at iodine, for instance, decaying. And iodine 131 means that's its total atomic mass number. If we look at the periodic table, we can see iodine has 53 protons. It's atomic number 53. So if it's going to undergo alpha decay, we draw an arrow. We draw that it's going to give up a helium nucleus as the alpha decay particle. Okay. And whatever is left over will be 4 lower in the top number. So we're looking at 127. And 2 lower in the atomic number. And if we look that up on the periodic table, that's antimony, Sb, and that's the element, and we know the symbol from the periodic table, just you have to look it up and see what's 51. And this is how we write out a alpha decay type reaction. We can check it and say 51 plus 2, does that equal 53? Yes. 127 plus 4, does that equal 131? Yes. So we know this is right. Beta radiation, this high energy electron that comes off, that occurs when a neutron, zero up there, turns into a proton plus an electron. So in order for that to work, what do we have? we have 0 and 1 for my neutron, right? Because it has no protons, and the protons plus neutrons is 1, so that's that. A proton is 1, 1 in terms of its atomic number and atomic mass number, because it has one proton, so that's at the bottom, and one neutron, or one total of neutrons plus protons, in this case just the proton, so it's 1, 1. So when we write the electron that it turns into, 1 and 1, the top number is already fine, so we don't want to add any more to the top number. But somehow we have to get back down to 0, even though we now have one proton here. So we give this a designation of -1 for its atomic number. And so electrons have an atomic number of -1. In this particular process, they're created by the formation of a proton and the loss of a neutron. And so in the grand scheme of things, you just have to remember this based off of balancing out this equation. It's a 0 -1 particle. So polonium, for instance, is going to turn into something by method of beta decay, meaning the emission of a beta particle. We have 218 over 84. When a neutron goes to a proton, it still has the same atomic mass number effect, right? Because we might have lost a neutron, but we've gained a proton. Lost a neutron, gained a proton. So the total of neutrons plus protons, same. So this top number is not going to change in beta decay. But the bottom number, we went from having a neutron to a proton, so the bottom number goes up by 1. Because we've just added a proton to this mix. And then we just simply write our electron of 0 and -1, and this balances. 84 is 85 minus 1. 218 is 218 plus 0. No big deal. Okay, so if we have carbon 14, carbon the 14 here means that it's the atomic mass number of 14, and the carbon on the periodic table it's listed as atomic number 6, so we know it has 6 protons. Write this out. We write out the electron that we know is going to be the beta decay particle. And that beta decay particle is going to then result in the exact same atomic mass number, but 1 larger for the number of protons, because we had a neutron turn into a proton plus an electron. So we look at the periodic table, that would be a nitrogen atom, so that's what we put in here. It's a nitrogen nucleus. And that's how we write beta decay or beta emission nuclear reactions. So we don't really write reactions for gamma radiation because this is just giving off energy. And so it's not giving off matter, but it's a very common form of radiation that occurs during other nuclear reactions. So we wanted to make sure we included it here in this chapter. So a couple other things we want to cover. One would be nuclear fission. So nuclear fission is where you force a atom to become larger by either putting another full atom's nucleus into it or by shooting neutrons into it. And so the idea is if you can force that to happen, and you can force beta decay to occur by just slamming something else into it like a neutron, then you might also end up with heavier elements. And what you could do is you could make elements that you wouldn't normally find just by taking really heavy large elements that are at the limit of what we actually find in nature and by bombarding them with things to make them larger. Wrong way. There you go. So uranium, for instance. If we fire a neutron at uranium-238, it can merge with and pick up that neutron. Well, now it's got this extra neutron, which makes it unstable. So 239 here instead of uranium-238. That lack of stability causes that neutron to undergo beta decay, meaning that it kicks off an electron, and that neutron turns into a proton. So we increase the size of that particular atom into a new element by just bombarding with neutrons and getting beta decay to then occur to the unstable nucleus, resulting in something with a number of protons that's greater by 1. In addition to this, we can actually see fission occur where the breakdown of what we've just made isn't quite so clean. It's not just beta decay, it's actually a disruption of that nucleus into a split of smaller nuclei. So uranium-235, for instance, when you bombard it with this neutron and it picks up, goes to uranium-236, and then splits apart to barium and krypton. When it does that, we actually end up with some free neutrons that are ejected as well. So not only are we adding a neutron, but now we're getting neutrons out of that reaction. Well, if those neutrons then go and strike additional uranium-235s, this reaction can happen again, and again, and again, and again, and again, and again, and again. And as long as you have enough of these to bump into, we can create more and more of this reaction process until eventually the amount of energy that's also coming out of this process as this occurs is a very large and overwhelming amount of energy. The original nuclear weapons were created by this sort of process. We've actually advanced on this a little bit, made this a little bit more sophisticated, but this is the idea behind a nuclear chain reaction. If you do this in a controlled manner, so that this happens only fast enough that you cause a lot of heat to develop, you can turn water into steam and power a steam turbine and get energy from this nuclear fission process in a fission reactor or a nuclear reactor. If you do this in an uncontrolled way, where the energy is rapidly evolved and given off at a really high rate of speed, you can cause explosions, which would be nuclear weapons, nuclear bombs and missiles and that sort of thing. Now, fusion has an even larger payoff in terms of energy. You, in this case, take light elements such as hydrogen, specifically the isotopes of hydrogen that are a little bit more rare, like deuterium and tritium, which are just the 1 neutron and 2 neutron containing versions of hydrogen. You fuse them together by slamming them into each other hard enough, or compressing them, or adding enough energy to make this happen. And when this occurs, you fuse the 2 hydrogens together to form a helium nucleus. The spare neutron is given off, and you release a freakishly large amount of energy that is way, way more energetic than even a nuclear fission reaction that's responsible for the original nuclear weaponry or nuclear reactors. Fusion is actually where the sun's gain its power. The gravitational force causing the friction and pulling the elements together is causing them to fuse, and when it fuses, you get heavier elements to form, and those heavier elements are giving off energy in the process, and voila, huge amounts of energy from the sun. Modern nuclear weapons also are based off of fusion type reactions. It's not the most efficient thing in the universe, but it gives the most amount of energy released per amount of material. So because of that, we can get much bigger explosions and kill far larger numbers of people, right? Like any good weapon is designed to do. So with controlled fusion, we can actually use this in a reactor. It doesn't have the same kind of radioactive waste products. The helium is not actually all that radioactive when you're done with it. And this gives us an unbelievable amount of energy that we could use to power all of the devices that we'll ever need to generate electricity or other energy for. Because deuterium, which is one of the main components in the tritium, that's the reactant for the fusion reaction to occur, is really abundant. And we have a lot of water on Earth, and even though only a small portion of it is deuterium and tritium, we have so much water that we can isolate that and have more fuel than we'll ever know what to do with for the immediate future. Now, the downside of this is, in order to cause this to occur in a nice controlled manner, requires instrumentation and temperatures and input of energy, which is very difficult to achieve. And then containing that energy in a way that doesn't melt down all of the stuff you just used to create that energy is also not an easy process. Right now, we can cause fusion to occur both in weaponry and in reactor type situations. But in order to cause that to occur, actually requires, at least in a controlled manner, actually requires more energy than we get out of it. So it's not really a viable method of generating energy at the moment, but it's a current area of research.